What if I told you that everything you thought you knew about power, about size, about the very limits of what a computer can be, was wrong? What if I told you that the colossal, room-sized supercomputers of just a few years ago, machines that cost millions, hummed with the power of a small town and were guarded in climate-controlled fortresses, could now sit on your desk, right next to your morning coffee? It sounds like science fiction, doesn't it? A fantasy. But today, we're not talking about fiction. We're talking about a tiny, shimmering gold box that defies logic, challenges physics, and promises to put the power of a data center directly into the hands of creators, thinkers, and dreamers. This is the story of the Nvidia DGX Spark, and it's a story that might just change everything. Let's set the stage. I want you to picture the year 2016. The world of artificial intelligence was exploding. Groundbreaking models were being born, but they were hungry, incredibly hungry for computational power. To feed them, Nvidia built a beast, the DGX-1. This wasn't a desktop computer, it was a monument to performance. The size of a mini-fridge, weighing over 130 pounds and consuming a staggering 3,200 watts of power. It was a beautiful, brutal machine, a server rack in a box that cost a cool $129,000. It was the tool that allowed companies like OpenAI to lay the groundwork for the AI revolution we live in today. For years, that was the price of admission. That was the scale you needed to work on the frontier of what's possible. Now, I want you to hold that image in your mind. The heavy, humming, power-guzzling mini-fridge. And now, forget it. Because what Nvidia has just unveiled is a paradigm shift so profound it feels like a prank. They call it the DGX Spark. It's a dense, metallic cube, smaller than a coffee mug. You can hold it in the palm of your hand. Let that sink in. A leap in computational density, so massive it's almost comical. It hell-s like taking a 1960s mainframe computer that filled an entire room and shrinking it down to the size of a smartphone while keeping all its power. This isn't just an upgrade. It's a redefinition of what a supercomputer even is. It's no longer a destination you rent time on in a remote data center. It's a tool you can own, a companion that sits on your desk. This tiny box isn't just an engineering marvel, it's a statement of intent. It's Nvidia declaring that the age of centralized, inaccessible AI power is over. The revolution will not be hosted in the cloud. It will be powered by a little gold box on your desk. But how on earth did they pull this off? The answer isn't just clever engineering, it's a fundamental rethinking of how a computer's brain should work. To understand the magic inside the DGX Spark, we have to dissect its soul. And at its very center, we find something that isn't just a new chip, but a new kind of life form in the world of silicon. It's called the Nvidia GB100 Grace Blackwell Superchip. Now that name is a mouthful, but what it represents is elegantly simple and breathtakingly powerful. For decades, computers have been built on a principle of separation. You have a CPU, the central processing unit, which is like the brilliant, logical, administrative brain of the operation. It handles tasks sequentially, manages the system, and runs the operating system. Then you have a GPU, the graphics processing unit, which is the creative, artistic, parallel processing powerhouse. It's designed to do thousands of simple calculations all at once, perfect for rendering graphics, or, as it turns out, the math that underpins modern AI. In a traditional computer, these two brains, the CPU and GPU, live in different houses. They are connected by a highway, a fast one, like a PCI bus, but it's still a highway. Data has to be packaged up, sent from one house to the other, unpacked, worked on, and then sent back. This constant back and forth communication creates a bottleneck. It is a fundamental traffic jam built into the very architecture of almost every computer on the planet. The GB100 Grace Blackwell Superchip obliterates this concept. This isn't two parts stitched together. Nvidia describes it as a single, unified brain. Imagine a mind with two distinct, hyper-specialized lobes. A 20-core ARM CPU for the logistical thinking, and a next-generation Blackwell GPU for the parallel creative work. but both lobes are part of the same consciousness. They don't need to send messages to each other. They share thoughts instantly. There is no highway because there are no separate houses. They live in the same skull. This fusion is more than just putting two chips on the same piece of silicon. It's a deep, symbiotic integration. The star of this show, the feature that makes this all possible, is its 128 gigabytes of unified memory. This is the key. This is the secret sauce. It's a concept so powerful and so game-changing that it deserves its own chapter. Because understanding unified memory is understanding why this little gold box can do the impossible. The article uses a beautiful metaphor to explain this, and it's so perfect we need to expand on it. Picture a vast, ancient library. This library represents all the information your computer needs to work on a task, like a massive AI model. In the old world, the world of traditional computers, you have two librarians. Let's call them Carl the CPU and Gina the GPU. Carl is a master of organization and logic. He sits at his desk and manages the entire library's operations. Gina is a savant of visual patterns and complex mathematics. She sits at her own desk, far across the room. Now, let's say they need to work together on a project, like generating an image from a text prompt. First, Carl receives the prompt. He processes it, figures out what needs to be done, and goes to the main bookshelf, the system RAM. He finds the relevant data, makes a photocopy of it, and then has to physically walk that stack of photocopies all the way over to Gina AS desk. Gina takes the copies. This is the data being copied to VRAM, does her incredible parallel processing magic, and generates the image. But if she needs more information, or needs to give Carl an update, she has to make her own photocopies and walk them back across the room. This process of copying and walking is a constant, time-wasting delay. And worse, if the project is a truly enormous one, like a 200 billion parameter AI model, it is like trying to work on a book so large that neither librarian S desk can hold all the photocopies at once. They're constantly running back and forth to the main shelf, swapping out pages, creating a chaotic and inefficient workflow. This is the bottleneck we talked about. Now, welcome to the world of the DGX Spark and its unified memory. In this world, there is no walking. There are no photocopies. Carl and Gina are sitting at the same giant table. In the middle of the table is one single, enormous book. The 128 GB pool of unified memory. When Carl needs to do something, he reads from the book. When Gina needs to work her magic, she reads from the exact same page of the exact same book at the exact same time. There is no delay, no copying, no data being shuffled around. They are accessing the same pool of information, the same single source of truth, instantly. This is why the DGX Spark can handle AI models up to 200 billion parameters. That massive complex model, the entire book, can fit on their shared table. The system doesn't waste a single nanosecond copying data between the CPU and GPU. It's an architecture of pure efficiency, designed from the ground up to eliminate the traffic jams that plague traditional systems. This isn't just a speed boost, it's a change in the laws of physics for computing. But to truly appreciate this new philosophy, we need to see what it's up against. We need to introduce the rival. Every great hero needs a formidable challenger, and in our story, the challenger is a familiar one. It's the champion of the old way, the pinnacle of the traditional approach, a custom-built, brute force AI workstation. Let's paint a picture of this beast. Imagine a sleek, massive tower case, lit with RGB lighting, humming with the power of a dozen fans. Inside, it's a monument to raw, unrestrained power. At its heart, a high core count CPU, maybe a Threadripper or a top-tier Intel i9, a processor with a voracious appetite for tasks. Supporting it is a vast sea of system memory. 128 gigabytes of the fastest DDR5 RAM money can buy. This is the central library we talked about. Huge and incredibly fast. But the real crown jewels, the source of its immense power, are the GPUs. Not one, but two Nvidia RTX 4090s linked together. These are the undisputed kings of consumer graphics cards, monsters of performance that, on their own, are more powerful than entire gaming consoles. Each one has 24 GB of its own dedicated ultra-fast VRAM. Together, they offer a staggering 48 GB of VRAM. This machine is a drag racer. It's built for one thing: pure, unadulterated, face-melting speed. If a task can be broken down and fed into those two GPUs, it will be annihilated in record time. For tasks like gaming, video editing, or training smaller AI models, this workstation is an apex predator. It is the embodiment of the more is more philosophy. More cores, more gigahertz, more VRAM, more power. But this champion has an Achilles heel. It's the very architecture that makes it so powerful. Despite its 128 GB of system RAM, its specialist librarians, the two 4090s, are still working off their own smaller desks. Their combined 48 GB of VRAM is their world. That is the size of the book they can comfortably work on at any given moment. So what happens when you give this brute force beast a task that's too big for its world? What happens when you ask it to work with a 120 billion parameter AI model? A dataset that is far, far larger than 48 GB. The system starts to choke. The lightning-fast GPUs are suddenly left waiting. They have to constantly ask the CPU to go fetch new pages from the main library, the system RAM, and swap them into their limited VRAM. This process, called memory swapping, is a performance killer. The drag racer is suddenly stuck in rush hour traffic. Its tremendous brute force is neutered by a fundamental architectural limitation. Its many specialized parts, no matter how powerful, can't overcome the time wasted communicating and copying. This is the classic showdown. The raw power of a muscle car versus the elegant efficiency of a Formula One racer. One is built for the straightaway, the other is built for the complex turns. Let's step back from the abstract world of memory architecture and talk about the physical object itself. The DGX Spark is not just a collection of powerful components, it's a piece of industrial art. Holding it feels like holding something from the future. It's a perfect metal cube, measuring just 150 by 150 by 50 millimeters. That's about 6 inches by 6 inches and only 2 inches tall. It's milled from a solid piece of metal, giving it a satisfying heft and a premium, cool-to-the-touch feel. This isn't a flimsy plastic box, it's an object of substance. The real artistry, however, is on the inside. Packing the power of a supercomputer into a space this small presents an immense thermal challenge. Power generates heat, and heat is the mortal enemy of performance. If a chip gets too hot, it has to slow itself down to avoid damage. A process called thermal throttling. So the engineers at Nvidia had to become masters of thermodynamics. When you open the Spark, you find an architecture of breathtaking density. The GB100 Superchip sits at the center, and surrounding it is a custom-designed, densely packed heatsink. Every square millimeter of space is utilized. Tiny fins and heat pipes snake their way through the enclosure, designed to draw every last watt of heat away from the chip's core. A single, high-performance fan then works to exhaust that heat out of the chassis. It's a miniature marvel of fluid dynamics and thermal engineering. And it's all powered by a single 240-watt USB-C power brick. Think about that. The same type of connector you use to charge your laptop or your phone is now capable of powering a desktop supercomputer. This single detail speaks volumes about the efficiency of the Grace Blackwell architecture. It sips power where older systems guzzled it. Now, the article does mention that early reports hint at power throttling for thermal control. Let's be real about what this means. It means that in the most demanding sustained workloads, the Spark might intelligently pull back its performance just a little to stay within its thermal limits. But this shouldn't be seen as a failure. It's a sign of a mature, intelligent design. It's the system protecting itself, ensuring longevity and stability. It's the marathon runner pacing themselves, rather than sprinting the first mile and collapsing. The true feat isn't just making it powerful. It's making that power usable and reliable in a form factor that is, frankly, unbelievable. When you look at the back of this tiny gold box, you get another clue that this is no ordinary computer. You might expect a couple of USB ports, maybe a display output, and you get those. Multiple USB-C ports and an HDMI 2.1a for modern displays. But then you see the other ports, and you realize this machine has a secret identity. First, there's a 10 gigabit Ethernet port. For context, most consumer PCs and laptops come with a 1 gigabit port. A 10 GB connection is 10 times faster. It's the kind of speed typically found in professional servers and high-end workstations, designed for moving massive datasets across a network without breaking a sweat. It is the first hint that the Spark thinks of itself as more than just a standalone machine. But the real giveaway, the ports that betray its data center lineage, are the two QSFP ports. QSFP, or Quad Small Form Factor Pluggable, is not something you find on a consumer device. These are high-density, high-performance network interfaces used in enterprise-grade switches and servers. Inside the Spark, these ports are powered by Nvidia AS-owned Connect X7 Smart NIC, a network interface card so advanced it's practically a co-processor in its own right. It can handle networking tasks at blistering speeds, freeing up the main CPU to focus on computation. So why would a tiny desktop box need this level of connectivity? The answer is as simple as it is ambitious: clustering. These ports allow you to connect multiple DGX Sparks together, daisy-chaining them into a single, cohesive computational fabric. With a simple cable, you can link two Sparks, and they will see each other and work together, effectively doubling your compute power and your unified memory pool. Link 4, and you have a 512 GB unified memory machine with the power of 4 superchips. This is the Spark's secret weapon. It's not just a mini data center, it's a modular mini data center. You can start with one, and as your needs grow, you can scale up, creating a desktop cluster with the power of a full server rack, all while taking up less space than a single traditional workstation. It's a true mini data center on your desk, a personal, scalable supercomputer. This transforms it from a powerful tool for an individual into a foundational building block for a small team, a research lab, or a startup. All right, the theory is impressive. The design is beautiful. But the real question is, how does it perform? It's time for the showdown. It's time to put the elegant, efficient DGX Spark against the brute force custom workstation in a head-to-head battle. The first test is the one the Spark was born for, the Large Model Challenge. The weapon of choice is a massive 120 billion parameter large language model. This isn't some lightweight toy AI. This is a serious data center class model, the kind that powers advanced chatbots and research projects. The task is inference, feeding the model a prompt and measuring how quickly it can process it and generate a response. First up, the custom workstation. The dual RTX 4090s roar to life. The fans spin up and the power meter starts to climb. The system tries to load the model, but it immediately hits a wall. The 120 billion parameter model is a book far too large for its 48 GB of VRAM. The system begins to thrash. You can almost hear it groaning as it frantically swaps data between the fast VRAM and the slower system RAM. The process is painfully slow and inefficient. When it finally manages to get running, the performance is crippled. The constant data shuffling creates a bottleneck that no amount of raw horsepower can overcome. The drag racer is stuck in gridlock, its powerful engine useless. Then it's the DGX Spark's turn. The small gold box sits there, silent. You press go, and nothing dramatic happens. The model loads seamlessly. The entire 120 GB plus model fits comfortably within its 128 GB unified memory pool. There is no swapping, no thrashing, no bottleneck. The CPU and GPU are looking at the same giant book on their shared table, and they just get to work. The results are staggering. The Spark processes the incoming prompts at a blistering 1,700 tokens per second. For context, a token is a piece of a word. So this is how quickly the AI can understand what you're asking it. Then it begins generating the response at a smooth and steady 38 tokens per second. This is the difference between a frustrating, laggy conversation with an AI and a fluid, real-time interaction. In the arena where size and architecture matter most, the DGX Spark doesn't just win. It delivers a complete knockout. It proves, beyond a shadow of a doubt, that a smarter, more integrated architecture can triumph over raw, disconnected power. Round 1 goes to the silent gold box. But the fight isn't over. A single victory doesn't decide the war. The second test is designed to play to the workstation's strengths. The task is fine-tuning, the process of taking a pre-existing, smaller AI model and training it further on a new, specialized dataset. This is less about memory capacity and more about raw, number-crunching throughput. This is the drag race the workstation was built for. The model is smaller this time, one that fits comfortably within the 48 GB of VRAM on the dual 4090s. The dataset is loaded, and the training process begins. This is where the custom workstation becomes a sight to behold. The two RTX 4090s, unburdened by memory limitations, unleash their full, terrifying power. They are specialist chefs in their own pristine kitchens, working in perfect parallel harmony. The sheer force of thousands of CUDA cores working in concert tears through the training data. The progress bar flies across the screen. This is what brute force looks like when it's allowed to run free. It's loud, it's hot, but my God, it is fast. Now the DGX Spark steps up for the same task. It performs admirably. The Grace Blackwell chip is no slouch, and it chews through the training iterations at an impressive pace. It's fast, efficient, and quiet. But it just can't match the raw, specialized speed of the dual GPU monster. The workstation, with its twin engines of pure horsepower, crosses the finish line significantly faster. And this result is just as important as the first one. It shows that the DGX Spark isn't a magic bullet designed to win every single benchmark. It reveals the core philosophy behind its design. It is a machine optimized for capacity and efficiency. It's built to handle the enormous models that were previously out of reach. The workstation, on the other hand, is optimized for raw throughput on tasks that fit within its limits. This isn't a story of one being definitively better than the other. It's a story of the right tool for the right job. But there is one final test, one that has nothing to do with models or tokens, but everything to do with the real-world experience of using these machines. The final test is one of practicality and livability. We've measured their performance, but what are they actually like to live and work with? Let's go back to the workstation during that fine-tuning test. When it was running at full tilt, it was consuming over 1,000 watts of power from the wall. That's the equivalent of running a microwave or a small space heater constantly, and all that power turns into heat. The dozen fans in its chassis weren't just for show. They were screaming, working desperately to expel a torrent of hot air into the room, raising the ambient temperature noticeably. The noise wasn't just a hum, it was a roar, a miniature jet engine that made it difficult to concentrate or even have a conversation. To use this machine at its full potential is to make a significant environmental sacrifice to your electricity bill, to the temperature of your office, and to your own peace and quiet. Now, let's look at the DGX Spark under its heaviest load. During the large model inference test, it was drawing a mere 100 to 120 watts of power. During the more intensive fine-tuning run, it might have peaked a little higher, but still nowhere near the consumption of its rival. This is less power than most high-end gaming monitors. And because it's generating so much less heat, its single fan doesn't need to work nearly as hard. Under a full load, it's whisper quiet. It's a gentle, unobtrusive hum that fades into the background noise of a quiet room. This is perhaps the Spark's most underrated and revolutionary feature. It delivers its incredible performance with an elegance and efficiency that is simply in a different league. In the crucial metric of performance per watt, the Spark wins so effortlessly, it's not even a contest. This matters. It means you can have a supercomputer in your bedroom or a small office without needing to upgrade your electrical circuits or invest in a new air conditioner. It means you can run complex experiments for days on end without worrying about an astronomical power bill. The workstation is a powerful but demanding beast that dominates its environment. The DGX Spark is a silent genius, a respectful collaborator that does its incredible work without making a fuss. It's a machine you can truly live with. So, after these 3 intense rounds, what's the final verdict? Who is the ultimate winner? The truth is, this was never a simple competition. This was a collision of 2 fundamentally different design philosophies. The DGX Spark, with its unified memory and integrated superchip, is the ultimate all-in-one kitchen. Imagine a master chef working in a perfectly designed space where the oven, the stove, the sink, and all the ingredients are within a single arm's reach. The workflow is seamless, efficient, and incredibly fast because no time is wasted moving between stations. This kitchen is designed to create vast, complex, multi-course meals, the massive AI models, with an elegance and speed that no other setup can match. The custom workstation, with its separate hyper-powered components, is the kitchen with specialist chefs. You have a world-class grill master and a world-class pastry chef. If you give the grill master a steak, he'll cook it faster than anyone on the planet. If you give the pastry chef a cake, she'll bake it to perfection in record time. But if you ask them to collaborate on a complex meal that requires constant back and forth, they have to run between their separate, specialized kitchens, and the whole process slows down. They are unbeatable at their specific focused tasks, but they lack the integration needed for the truly massive holistic projects. The DGX Spark wins the war for large-scale, next-generation AI workloads. The workstation wins the battle for smaller, brute force-dependent tasks. But Nvidia AS' goal here was never to simply replace the power rigs that gamers and VFX artists love. Their goal was to redefine what's possible on the desktop. They built the Spark to solve a problem that, until now, had no desktop solution. It's not about making existing tasks a little bit faster. It's about making previously impossible tasks suddenly achievable for everyone. So, who is this little gold box actually for? When you boot it up, you're not greeted with Windows or Mac OS. You're welcomed into a preloaded, AI-optimized Linux environment, packed with NVIDIA's CUDA libraries, containers, and development tools. This is the first clue. The DGX Spark is, first and foremost, a developer platform. It's for the university researcher who has a groundbreaking idea for a new AI architecture, but can't get enough time on the university AS overloaded server cluster. It is for the small startup with a brilliant idea for an AI-powered service, but lacks the venture capital to rent expensive cloud-based GPU instances from Amazon or Google. It's for the indie game developer who wants to create non-player characters with truly intelligent, unscripted behavior, powered by a large language model running locally. It's for the digital artist who wants to fine-tune their own generative models on their personal art style, iterating and experimenting in real time. The DGX Spark is designed to be the ultimate bridge. It bridges the gap between desktop experimentation and enterprise-scale deployment. A developer can now build, test, and iterate on a massive model right on their desk in a quiet, low-power environment. Then, when the model is perfected, they can take that exact same code and deploy it to the cloud, or a larger DGX system, with the confidence that it will scale perfectly. It removes the friction and the immense cost that has, for years, been a barrier to entry for so many brilliant minds. It's a tool for innovators, for pioneers, for the small teams who dream of competing with the giants. It's a machine designed not just to run code, but to empower dreams. In the end, the story of the DGX Spark isn't a story about benchmarks. If you just look at the numbers, you might miss the point. This machine wasn't built to win every speed test. It was built to break old limits. For decades, we've defined a computer's power by its speed, by its gigahertz and its teraflops. But perhaps that's too narrow a definition. What if we define a supercomputer, not by how fast it can run an old task, but by its ability to empower us to tackle entirely new ones? What if a supercomputer is simply a machine that makes the impossible possible? By that definition, this little gold box is a true revolution. It democratizes access to the cutting edge of AI development. This is more than just a new product. It's a gateway. It's a key that unlocks a door that has long been closed to most of us. The DGX Spark is a bet on the power of individual genius and a testament to the relentless march of progress, turning the once unreachable into something that fits in the palm of your hand. The lesson from this story, for me, is about looking beyond the surface. It's a powerful reminder that in technology and in life, brute force isn't always the answer. Smarter, more elegant, more integrated design can often solve problems that raw power can't touch. It encourages us to ask not just how fast can it go, but what new places can it take us? The advice we can draw from this is to always question the old way of doing things. Just because a problem has always been solved with a bigger hammer does not mean a cleverly designed key won't work better. And that brings me to you. This technology is no longer science fiction. It's here. So I want to ask you, what would you do with this kind of power on your desk? What impossible problem would you try to solve if the barriers were suddenly removed? Would you build a more compassionate AI therapist, a creative partner to help you write a novel, an intelligent system to help us model climate change? Let me know your dreams and your wildest ideas down in the comments below. I truly believe we're at the dawn of a new era of creativity and discovery, and I can't wait to see what you all build with it. Thank you so much for joining me on this incredible journey today. I wish you all the very best of health and happiness. And if you found this story as fascinating as I did, and you want to stay on the cutting edge of technology that is changing our world, do me a favor and hit that like button, and be sure to subscribe to the channel so you don't miss what's coming next. Until next time.